Today we're diving into ColibriTD's HDES, and we're going to meet cat qubits from the French quantum startup Alice and Bob. Starting off with, and very excited to present, Boyle. Dr. Boyle spent almost a decade as a researcher in theoretical cosmology before developing an interest in quantum computing and joining the research and development team at ColibriTD. Her work involves the development of quantum algorithms with a particular focus on potential applications in climate modeling. She joins us today from Paris to tell us about ColibriTD's HDES, which is a universal quantum solver designed to tackle partial differential equations for real-world applications.
Thank you, Katie. Thank you all very much for joining, and thank you very much as well for the invitation to give this talk. I'm a quantum algorithms researcher at ColibriTD, which is a quantum computing software company based in Paris. And today I'm going to present one of our quantum algorithms, our hybrid differential equation solver, or HDES. I'll also talk briefly about our company and the current era of quantum computing and where we're planning to go in the future. So I'm very aware that many of you that are joining probably have a background in quantum, but from what I saw, there's a bit of a variation in experience level among the audience. So I just have a couple of slides on quantum computing for people who are more in the sort of beginner phase. So quantum computing is based on the concept of a qubit, and a qubit or quantum bit is the basic unit of quantum information. It's analogous to a classical bit, but with unique quantum properties that arise from the principles of quantum mechanics. So unlike classical bits, like in your computer at home, which can only be in one of two states at a time, either 0 or 1, qubits can be in a superposition of the 0 and 1 states simultaneously. And ultimately, what this means is that the information that's carried by a system of qubits grows exponentially with the number of qubits. And this is the expected advantage of quantum computing over classical computing and why there is so much excitement about it. Also, analogously to classical computers, quantum computers have quantum circuits, and these are sequences of quantum gates that are applied to qubits to manipulate their states and perform calculations. And you have an example here of a quantum circuit on the left. So where is quantum computing today? Well, currently we're in what is known as the noisy intermediate scale quantum, or NISQ era. And what this means is that we have quantum computers that are functioning and they're being used to perform calculations, but they have limited qubit numbers, so they're of intermediate scale, and they're also prone to errors, so they are noisy. And the goal ultimately is to achieve full fault-tolerant quantum computers. But in the meantime, while we wait for that, NISQ devices are still very useful for developing and testing quantum algorithms, and they may solve some problems more efficiently than classical computers. And there are many possible applications of these NISQ computers in all kinds of domains, in finance, in optimization, in science, machine learning, and so on. At ColibriTD, our focus is on industrial simulation. And specifically, we're very interested in variational quantum algorithms, or VQAs. And the algorithm that I present today belongs to this class of algorithms. And VQAs are quantum algorithms that are designed specifically for the NISQ era. What this means is that basically, while quantum computers remain limited, VQAs make use of a hybrid quantum classical approach, where they combine quantum and classical computers to work together to solve problems. And I know that this talk is part of a series on differential equation solving. So I think for a lot of the audience, you're very comfortable with the motivation for this kind of work. But for anyone who's new and might be asking why do we care about partial differential equation solving? Well, essentially, partial differential equations lie at the heart of modeling and predicting complex phenomena in nature. Basically, anywhere where you want to know how a field evolves in space and time, you can probably describe your system using partial differential equations. And this means that partial differential equations, or PDEs as I'll call them, underpin virtually all modern simulations in many different domains. The problem, however, is that many PDEs are very difficult to solve, especially for very large and complex systems. And this creates bottlenecks in the advancement of many fields in science, in technology, and in medicine, for example. And the reason for this is essentially that the scaling properties of classical PDE solvers are very poor. Generally, if you have a simulation and you increase the number of dimensions or the number of variables or the resolution that you require, you incur an exponential increase in computational cost, so in the time that it takes to solve your problem. And what this means ultimately is that many important systems that we would like to really analyze in detail remain impossible to simulate on feasible timescales without approximations or low resolution or other adaptations. So HDES, as I said, is the name of our algorithm, the hybrid differential equation solver. And these are just its main characteristics. I'll go into these in more detail on the coming slides. But essentially, HDES is a generic solver for any system of partial differential equations. So this means, in theory, it's one algorithm that can be applied to do any kind of multiphysics simulation. It's a hybrid quantum classical algorithm, as I hinted at before. And what this means is that it makes the most of the quantum computers that we have today and combines them with classical computers to exploit the advantages of both. And this also means that it's an algorithm that can be run on the quantum computers that already exist today. And later in this talk, I'll be able to show you some results from that. HDES is based on a spectral decomposition method. This is one of the nice features that makes HDES incredibly resource efficient. I'll explain this in more detail on some coming slides, but all you need to know for now is that ultimately this means it requires a very low number of qubits to achieve a very high precision solution to a simulation problem. HDES is currently under review, so there is an article on HDES that's currently under review, but in the meantime, the article is available freely on the archive if you're interested after this talk in diving into HDES in more detail. And there's also a patent pending on the HDES algorithm. So this slide just gives you an overview of how HDES works. And on the coming slides, I will give you more detail on each of the components that are shown in this slide. But basically, the user first starts by inputting a set of partial differential equations that define the system that they're interested in simulating. And they also pass in a set of boundary conditions, which includes usually initial conditions. So this could be, for example, a set of partial differential equations that represent a fluid dynamics problem or a mechanical problem or an electromagnetism problem. The possible applications are very broad. And the process of finding a solution to the set of PDEs with HDES then involves an iterative process between a quantum computer and a classical computer. So within the quantum computer, trial solution functions, so attempt solution functions to the problem, are encoded in quantum state vectors. And these quantum state vectors are generated when a quantum circuit is applied to a set of qubits. And this quantum circuit is a parameterized quantum circuit. And what that means is that the gates of the circuit can be altered externally. So a classical optimizer on the classical computer determines the parameters that define these gates. Every time an attempt solution is generated, the classical computer substitutes the solution into the equations to evaluate a loss function that determines how well the trial solution function fits and how well it matches the boundary conditions. And the classical optimizer then updates the quantum gate parameters based on these results to create a new trial solution. And this iterative process between the quantum computer and the classical computer, this hybrid loop, continues until a good solution is found. So essentially, there are four main ingredients for the HDES algorithm. There's a parameterized quantum circuit on the quantum computer. There's a trial solution function to the set of PDEs, or several trial solution functions, encoded in quantum states that are generated by parameterized quantum circuits. There's a cost function that guides the optimization process, and then there's the classical optimizer itself. And the main advantages to VQAs, I mentioned this briefly earlier, but essentially VQAs are very useful for NISQ devices because you can achieve a lot with quite low depth circuits. By low depth, I mean that you don't have too many gates in sequence in your circuits. And lower depth circuits are much less susceptible to noise. And obviously VQAs also, they use the best of both classical and quantum computers. That's another advantage. So now I'm going to go for each of the 4 ingredients of the algorithm that I mentioned on the previous slide. Now I'm going to go into a bit more detail on each of these. Depending on your level, I think most of you will be fine. For some people, it might be a little technical, but after these slides, I'll show you some really nice results. So the role of the parameterized quantum circuit, first of all, is essentially to convert the classical optimization parameters, so these theta, into a quantum state vector, this psi, that encodes a trial solution function or functions to the set of partial differential equations. So this little bit of maths here on the bottom left summarizes this. The quantum state vector is essentially the result of applying certain gates that depend on these optimization parameters to a set of n qubits in the 0 state to output quantum state vector with 2 to the power of n elements. And the image on the right shows an example of such a circuit. This particular structure that we use in HDES has a name. It's called the hardware efficient ansatz. And for those of you that are already quite familiar with quantum computing, you'll recognize a series of RY rotational gates and C0 gates. And it's the rotational parameters of the RY gates that are externally adjusted by the classical optimizer, while the C0 gates create entanglement among the qubits. And the hardware efficient ansatz is chosen because it's a type of ansatz that has very high expressibility. And what this means is that with only a few layers, it can produce a wide variety of possible state vectors. So it allows us to probe a lot of possible solution functions. There's other reasons. It's less prone to errors, so it's very suitable for NISQ devices. It uses native gates and nearest neighbor entanglement and so on. So it's very suited for the quantum computers that we have today. So I told you on the last slide that we use a quantum circuit to prepare a quantum state vector that represents or encodes a trial solution function to the system of PDEs. But what does this mean in practice? Well, the solution is defined as a spectral decomposition. What this means is that basically you adopt a set of orthogonal basis functions and you define your solution function as a linear combination of these basis functions as shown here in this little equation. And the coefficients of these basis functions in the sum are what the quantum state vector provides. The most common basis functions that we use are the Chebyshev polynomials of the first kind. And the first few Chebyshev polynomials are shown here on the right. And the basic idea is that because these functions are orthogonal, we can represent any solution function if we have a sufficient number of Chebyshev polynomials through this kind of linear combination. We don't always use Chebyshev polynomials, but it's our most basic go-to basis. So this slide just adds a bit more detail. Essentially, the coefficients of the Chebyshev polynomials that are used to describe the trial solution function are extracted from the prepared quantum state vector. So the trial solution, f of x, is reconstructed using the probabilities of the set of qubits being in each quantum state. Now, the most important thing to note here is that in our encoding, n qubits can provide a solution constructed from 2 to the power of n minus 1 Chebyshev polynomials. And what this means is that every time you add a qubit to your system, you double the number of Chebyshev polynomials in your solution. And what this means is very precise results can be achieved with only a handful of qubits. So at the bottom here, we have a very simple example for 2 qubits. So with 2 qubits, we have 4 possible states and 4 amplitudes in our prepared quantum state vector, of course. Because we use the probabilities as the coefficients in the spectral decomposition, because probabilities are always positive, we have to allow for the possibility of negative coefficients. So we use half of the states to allow for this possibility. So in this simple case, our possible results only have the form of a line because we only have 2 qubits and 2 Chebyshev polynomials. However, the number of Chebyshev polynomials in the decomposition increases exponentially with the number of qubits. So once we go from 2 qubits to 3 qubits, our potential solutions will be polynomials of order 3 and so on. And this slide just shows how the trial solution functions are extracted in practice using the expectation value of an observable. This is the observable here, this OC at the bottom. And it's important to emphasize that we can easily modify this observable to extract derivatives of the solution function instead of the function itself. And the way that we do that is by replacing the Chebyshev functions on the diagonal of the observable with the derivatives of the Chebyshev polynomials for which there are analytical formulations. And this gives our approach a rather unique advantage over other methods, which is that we can compute the derivatives of our trial solution functions exactly. And of course, this is very important for solving partial differential equations to high accuracy. You don't want to use some kind of differentiation scheme that can introduce numerical errors. And in fact, in many cases, integrals of the solution functions can be extracted using a similar approach. And this allows us to apply our method to integral differential equations as well, and it makes our algorithm even more general. Of course, everything basically that I've shown here so far is for the one-dimensional case, so what we call normally ordinary differential equations, but this can be straightforwardly extended to higher dimensional simulations quite easily. So the third ingredient of the algorithm is the cost function. And of course, this is what the classical optimizer uses to determine how close it is to a given solution and to determine its optimization path. So after each evaluation of the solution function, this cost function is evaluated. And it consists of two parts. In the first term, the solution function and its derivatives and other components of the equations are plugged into the set of differential equations to see how well they satisfy them across a chosen number of sample points. In the second term, the difference is taken between the trial solution function at the boundaries and the required boundary conditions. So the goal of the optimizer, of course, is to minimize the sum of these components. And when the cost function gets close to zero, it means that the differential equations and boundary conditions are both very well satisfied and you have a good solution. In practice, for more complex problems, we often take a slightly different approach and we build the boundary conditions into the structure of the problem in various ways. This means that then we only have to worry about solving the differential equations and the loss landscape is simpler. But for the purposes of this talk, we just focus on this more simple formulation. And if you want to know more about other methods of handling boundary conditions, you can refer to our paper. Fourth ingredient, the final ingredient, is the classical optimizer itself. And this is either the simplest or the most complicated component, depending on how you want to look at it. So it's the simplest in the sense that this is a very well explored area of machine learning, and there are a huge number of options available in packages like SciPy and so on. It's the most complicated for exactly the same reason. There are a huge number of possible options with different advantages. And the role of the classical optimizer is simple. It uses the information that it receives from the cost function to determine new parameters, to pass to the quantum circuit to generate a new trial solution function, and it continues until a good solution is found. So you might be asking, how many parameters do we usually have to optimize? Generally, it's quite low, especially compared to classical analogs of this problem or this algorithm. So we often see our algorithm as kind of a quantum version of something called physically informed neural networks, or PINs. And in the case of PINs, thousands of parameters usually have to be optimized. And in our case, because of the low number of qubits and the low depth circuit that we adopt, for the results I'm going to show you later in this talk, the number of parameters to be optimized is maybe 100 to 150 maximum, and often less. So now I've gone into more detail on the four main ingredients: the parameterized quantum circuit, the encoding of the solution functions into a quantum state, the cost function to guide the optimizer, and the optimizer itself. And I think the most important thing to emphasize here is that each of these components is very flexible. So for different problems, we can and do adapt the encoding of the solution function, the cost function, the optimizer, the circuit, the basis, all other features of the algorithm to different kinds of problems and simulations. And this means that our algorithm overall is really very, very flexible. So here, I just tried to summarize the main characteristics of HDES once again for solving PDEs. So first of all, it's a generic solver for any linear or nonlinear coupled system of partial differential equations and any boundary conditions. And only one circuit is needed in the HDES algorithm to represent a solution function and all of its derivatives. And these derivatives are computed exactly, as I said before. So again, this makes it a very resource efficient algorithm. Furthermore, only a few qubits are required to achieve a high precision solution because of our use of a spectral method. And this is in contrast to, example, grid-based methods. And we can run our algorithm with very reasonable depth circuits, which makes our algorithm very noise resilient. So these latter 2 points mean that our algorithm is already functional in the NISQ era of quantum computing. So if one question that might come up is for basically the results I'm going to show you in this talk, most of them are easily computable with classical computers that we already have. So why are we interested in going to all this trouble with a hybrid quantum algorithm to replicate the same results? And the answer is basically because of HDES's scaling properties. So I told you at the start of this talk that for classical simulation problems, we have an issue which is known as the curse of dimensionality. And this means that for classical simulations, for most methods like finite element methods and so on, when you increase the complexity or dimensionality of your problem, when you add variables or want to increase the resolution, you incur an exponential increase in computational cost. And the time required and cost required to run your simulation becomes very dramatically greater. For HDES, on the other hand, the scaling properties are much, much more promising. So to start with, the number of qubits required only grows linearly with the number of equations and variables for a given precision. So this is in contrast to exponentially. Secondly, the number of basis functions in the spectral decomposition grows exponentially with the number of qubits. And this is what I showed you already. So basically, every time you add another qubit, you get twice as many Chebyshev polynomials to construct your solution function with. The number of parameters to optimize grows at most quadratically with the number of qubits, which is quite conservative, especially as we don't need many qubits. Fourthly, and this one I think is really important to understand, because of our use of a spectral method, we can basically, so with classical simulation methods, they're usually performed on a grid. And if you increase the resolution of that grid, the computation becomes much, much more difficult and more lengthy. In this case, with HDES, increasing the number of sample points effectively has only a negligible effect on the computational cost of the algorithm. So basically, once you solve your system of equations, you can sample the solution as heavily as you want down to essentially numerical precision. So basically, you can get very high resolution results without increasing the computational cost. And what all of this means is that HDES should provide very significant advantages over classical solvers once it's scaled up to bigger problems. So basically, once we have problems with very large dimensionality, a lot of variables, or a need for very good accuracy. Now, this scaling up of HDES is currently probably the primary focus of our research and development team. And there are certain challenges associated with scaling up VQAs to tackle more difficult problems. And in particular, the most difficult is that when you have a large number of parameters to optimize, you have to be able to ensure that you have a well-behaved loss landscape for the problem to be optimizable at all. In particular, there's a problem known as barren plateaus. And a barren plateau is essentially a flat region in the loss landscape that can occur when you have too many qubits and the gradient of the cost function becomes extremely small. And what happens in this case is that the optimizer essentially gets stuck. It doesn't know how to optimize further. But for this, we're working quite hard on overcoming this issue, and we have a lot of promising early results. And basically we're exploring different options for this barren plateau problem, and they include, for example, problem-informed ansatz, initialization strategies for the parameters so that we start the optimization process in a good place in the lost landscape, certain modifications to the observable, and so on. And yeah, there's a lot of literature on this barren plateau problem, so we're quite confident that we're going to gradually scale up into bigger and more complex problems. Okay, so that was the introduction to the algorithm, and now I will show you some results. First, I'm going to show you some results that we've achieved on real quantum computers. Then I'll show you some results that are a bit more ambitious, and so far the more ambitious results, we've only achieved them on quantum simulators, but we're planning to replicate them on real quantum computers very soon. So the HDES algorithm was under development for several years before we started to run it on real quantum computers. And during that time, we used quantum simulators instead. And we still use quantum simulators to do the vast majority of our research and development work because it's much cheaper. Oh, sorry. It's much cheaper and easier for now. However, we're very lucky to have several great hardware partners, including IBM and AWS. And between them, they've given us hundreds of thousands of euro of free time on their quantum computers over the course of the last year, because they really believe in the potential of our algorithm. So IBM asked us to demonstrate that our algorithm could be used to solve a fluid dynamics problem and a mechanical problem on their quantum computers. And that's what we did, and that's the results I can show you now. So this is a result from our first round of time on IBM's quantum computers. And here we tested our algorithm by solving a computational fluid dynamics equation called the Inviscid-Burgers equation. And this equation is used to model the evolution of wave-like phenomena where nonlinear advection dominates and there's no viscosity. So it's often used to study shockwave formation, and it has applications in fluid dynamics, gas dynamics, traffic flow, and so on. And the solution function shown here on the right is the wave velocity as a function of x and t. And what you can see is that the result from HDES matches the analytical solution very well. So this is not my plot, but I think the sort of plane here is the analytical solution, and the dotted lines are the results from the IBM quantum computer using HDES. So there's a very good match, and this was quite a significant result for us at the time. It was the first time that a simulation like this, a fluid dynamic simulation like this was done with, sorry, my slides keep skipping. It was the first time that a simulation like this was done with this kind of a general solver, VQA solver on a quantum computer. So we had a little press release. And the GIF on the left just shows a little part of the convergence process for one slice of the solution. And you can see the blue color is the correct solution, and the teal line that's kind of jumping around shows the optimizer's attempt to find the correct solution. And I think it's just nice to see how the optimization process progresses over time. So we also recently joined the Qiskit functions catalog. So for anyone who's not familiar with this, it's quite interesting. It's basically a catalog of algorithms that IBM makes available to its paid users to test on their quantum computers. So this version of HDES is available. The version of HDES that's available in the Qiskit function is limited. It can only be run for two specific use cases, and one of those use cases is this one, to run the Inviscid-Burgers equation. However, it doesn't mean that you replicate exactly this result. The user has the option to vary the boundary conditions and the initial conditions to produce different results for different setups. And this was a really nice step for us so that we can get feedback on the algorithm's performance for the first time from outside the company. Now I'll present the second set of equations that we solved for IBM. So this set of equations represents a more mechanical problem. Specifically, it simulates the hypoelastic deformation of a bar under strain. The results on the right show the final result for the displacement of the bar and the strain on the bar as a function of x. And you can see that the result is quite a good match to the analytical solution here, except for U perhaps at high X, where there's a bit of a divergence. And this is just the result of noise on the machine. And to address this long term, there are obviously two avenues. Obviously, the hardware is improving at an incredible rate on the IBM side. And on the other hand, we can also explore noise mitigation and error correction techniques to further improve the results. But anyhow, these results are quite promising nonetheless. And this use case is also available in our Qiskit function, so users are able to replicate these results on IBM quantum computers themselves. So now that I've shown you how HDES works on real quantum computers, I'll show you some of our more recent results from quantum simulators. So these are results that we hope to run with our next round of credits from IBM and AWS. So because HDES is a general multi-physics solver, we have a lot of different projects at Colibri focused on different domains, aerospace, fluid dynamics, materials, finance. And I'm lucky enough to be the leader of a project called Quantum for Good. And with this project, we focus on areas where we hope that HDES can have a more positive impact long term. And more specifically, the current goal of Quantum for Good is to extend HDES for climate modeling. And this is an important point of focus in the simulation world because climate simulations are incredibly complex. They include virtually all kinds of physics in coupled systems, and they deal with an incredible range of physical scales and timescales. But accurate climate simulations are critical for for example, mitigating the impact of climate change and for optimally exploiting renewable energy resources. So although we're a long way from full climate simulations, it's important for us to start exploring this domain as quickly as possible. And for this work, we have two major research partners, the European Space Agency, ESA, and also Cinica, which I think is Italy's largest HPC center. So here's an example of the simulation of a climate relevant system using HDES. So convection and diffusion are processes that occur everywhere in physics, but in the context of climate modeling, we're specifically interested in their relevance to the movement of, for example, heat and pollutants through the atmosphere and through oceans. And so this toy model shown in the animation is a 3D or 2D plus time, I should say, model. Essentially, what you can see is the simulation of a convection diffusion process. So we start with an empty domain at t equals 0, and there's a source in the center that emits a substance at a constant rate. And there are positive forces acting in the rightward and upward directions, and these can be considered the effects of a current in water, for example, or the effects of a wind in the atmosphere. And you can see that the result behaves exactly as we would expect. So the concentration of the substance increases over time, and the peak of the concentration moves upwards and rightwards as time passes. And there are wall-like boundary conditions that confine the concentration to the domain. Sorry. And the results here, they match the results from classical simulations very, very precisely. And what I think is really incredible to emphasize is that this simulation here in 3 dimensions was done with a total of 8 qubits, which is an incredibly low number. So I think it's really a really nice result of our HDES algorithm. And as I said, we're hoping to run this very soon on quantum computers, probably from IBM, to replicate the result there. This is another example that I really like from our Quantum for Good project. So the shallow water equations are used in climate simulations to model catastrophic events like tsunamis and floods. Essentially, they're a version of the Navier-Stokes equations, which you're probably familiar with, but they're reduced by 1 dimension. So we derive the shallow water equations by assuming that the motion of water in the vertical direction in the Navier-Stokes equation is negligible compared to the movement of water in the horizontal direction, so hence shallow water equations. And this plot here on the left shows a solution for the shallow water equations achieved using HDES. Again, I should stress on a quantum simulator for now. If you focus on the top panel, this shows the water height. And the lower panel is the corresponding water velocity. But in the upper panel, we can see that the initial condition is a flat water surface, with a large perturbation in the center. And as the simulation evolves, we can see that this behaves exactly as we would expect water to behave under the influence of gravity. So I'll just let it restart. Sorry, it keeps skipping forward on me. But basically, the water behaves exactly as we would expect. So the perturbation falls, the water falls, it splits into two symmetric waves. And these waves then move outwards towards the edges of the box. They reflect off the boundaries of the domain and they bounce back. And this simulation was done, I believe, using 12 qubits. So the next step is to extend this to 2D plus time, like I had on the previous slide. And this represents full dimensionality for the shallow water equations because they don't have a vertical direction. So that would bring us very close to a real practical use case. So I'm very excited about that. This slide essentially is just to give you a summary of the different kinds of equations that we can solve and have solved, both mathematically and also in terms of use cases. So it's slightly out of date because it only shows 1D and 2D, and we have 3D simulations that we could add here now. But you can see that there are all kinds of problems that are considered here. So like different fluid dynamics equations, combustion equations, mechanical problems like dynamical problems like harmonic oscillators and so on. And for going further, what we want to do, what we're really driving for now is to solve more complex problems with HDES with a higher number of dimensions and larger simulation scales so that we can really take advantage of all of those scaling properties of HDES that I showed you earlier. Yeah, just before I finished, I've lost my timer, but I think I was just about out of time. But I just want to tell you briefly about another project that we have at Colibri that I think will be interesting to all of you and is also very relevant to us, and that's called MPQP. So MPQP it's a programming library, Python library, that basically exists to resolve a very specific problem. And that problem is that at present, there are more than 70 quantum hardware providers on the market. And you can see some of these shown here on the right. And each of these providers has their own way of communicating with their machine. So this is called an SDK. So you might be familiar with, for example, Qiskit and Bracket. And this can be a bit frustrating if you're trying to develop quantum algorithms and run them on quantum hardware, because it basically means that every time that you interact with a new piece of quantum hardware, you have to rewrite your code to deploy your algorithm. So at Colibri, we developed a programming library called MPQP. It stands for Multi-Platform Quantum Programming, that lets you basically code your algorithm once and then deploy to any of the major quantum hardware providers. So the nice thing about MPQP is that it's open source, so you can use it as freely as you want, and you can find it on GitHub. And you can also talk to us, give us feedback on how it is, and contribute if you're interested. It was developed originally to support our R&D team, and then we kind of made it a gift to the quantum community. And MPQP is something that I really recommend. And the HDES code itself that we use here is written in MPQP, and that allows us to deploy it to all kinds of different quantum computers because we have many quantum hardware partners. And this slide, this is my second last slide, I promise, summarizes basically where we want to go with HDES as a company. So probably if there's any engineers in the audience in particular, but also physicists and computer scientists to a degree, you might know about classical multiphysics simulation software like that produced by ANSYS or COMSOL. And long term, we hope to actually produce essentially a quantum version of this. And the idea is that we'll build a platform which will be called QUIC, which stands for Quantum Innovative Computing Kit. And the idea is that an engineer or someone else with a multiphysics problem, a scientist who wants to perform a simulation, will be able to run simulations using HDES on quantum computers without having to learn about quantum computing themselves. So basically, they will have access to this platform through a license, and they will have modules that they can choose from for different kinds of physics and different kinds of problems. And under the hood, QUIC will solve these problems using the HDES algorithm that I presented to you today. The algorithm is written in MPQP, and then they will have the option to deploy their computation to any of our hardware partners. And Yeah, this is my last slide. So I included here just a little picture of the team at ColibriTD. You can see that it varies a bit. We're about 20 people now. We're based in Paris. At the moment, we're based in Station F, which is the largest startup campus in the world, I believe, definitely in Europe. And so if you ever want to stop by and visit us, feel free. Then you can follow this QR code for our website, and there's some contact information here for me and for the company. So thank you very much for listening, and I hope this was interesting, and I look forward to your questions.
Thank you so much. So I think some of the questions have come through on Discord.
Okay, hold on. Let me see. Oh, I see the questions. So first, someone just posted the paper. Thank you very much. That's really nice. And then there's a wave. That's also really nice. Does the cost function ever get stuck in local minima? Yes, in fact, this does often happen. And this is a big focus of our R&D team, is basically figuring out ways to prevent that. So there are quite a few approaches that you can take to try and address this problem. So for simple simulation cases, in general, it doesn't really happen. But for very complex problems, it can. And I'll just give you a few examples of things that you can use to solve this issue when it occurs. One, for example, would be the optimizer itself. Some optimizers, the name escapes me right now, have a concept called basin hopping, I think, where basically if the cost function gets stuck in a local minima, it can like jump randomly to other places in the lost landscape and kind of escape. And there are other optimizers that can escape from local minima in other ways. There are also other approaches. So with HDES, because we have an optimization process, we think a lot about basically initialization strategies. And what this means is strategies that we can use. So generally when we use HDES, the parameters that the classical optimizer starts with are just randomly generated using NumPy. But it is possible to choose your parameters, your starting parameters in certain clever ways to make it more difficult to get stuck in a local minimum, essentially. And you can do this by taking into account different aspects of the problem, for example. And that's all I can say on this for now, I think. So there are solutions to the local minimum. There are various solutions to the local minimum problem, yes. I hope that's enough of an answer for you for now. But the answer to your question of whether they get stuck is yes, indeed, sometimes. Then the next question is, what differentiates the HDES approach from quantum physics informed neural networks? So I don't think I'm personally familiar with specifically quantum physics informed neural networks. I'm a bit familiar with PINs, so the classical version of physics informed neural networks. And basically what I would say is that what we find to be the advantage of our algorithm over the classical physics informed neural networks is that we generally need far fewer parameters to complete the same calculation. So we actually did a direct study on this where we had someone working with the company who was trying to replicate our results for a specific equation using a physics-informed neural network. And they needed much, much more parameters, optimization parameters, to be able to reproduce the same result. So that shows that this quantum part really does contribute something. The next question, all the scalings you mention is about mapping. I'm a bit confused about the meaning of the next question. And I'll just pass over it for now if that's okay. The next question is, how do the Chebyshev polynomials make such good partial differential equation solvers compared to Fourier? So, okay, this is a question about the choice of orthogonal polynomials or orthogonal basis functions. And the reason that we started with Chebyshev polynomials, as far as I'm aware, is that they were very widely used in the literature for the kinds of problems that we were considering at first. But we don't use Chebyshev polynomials all the time. For example, for the shallow water equation results that I showed you, I actually use something closer to a Fourier style basis. So in a sense, the basis can be adapted to the problem at hand if you have some kind of intuition about the equations and about the general solution functions. like the form that the solutions to that set of equations often take. You can work backwards from this to choose another basis. So this is fully flexible, but in general, we start with Chebyshev polynomials. Someone wrote that it was very insightful. They liked the talk. Thank you very much. The next question, is it possible to quantify the impact of increasing the dimensions of space? To quantify the impact of increasing... Yeah, so I hope I understand your question properly. Generally, what we find, this is for Mohammed Reza, generally what we find is that the number of qubits required scales linearly with the number of variables. So if you think back to the 2D plus time convection diffusion system that I showed you, when I solved this in 1D plus time, I needed around 6 qubits. No, 5 qubits. Yes. And then when I solved it in 2D plus time, I just had to add 3 more qubits. So yeah, then I had 8 qubits, and I'm pretty sure that I want to try and solve it now in 3D plus time, so like full dimensionality, and I think that can probably be achieved with like 11 or 12 qubits. So basically, the number of qubits that you require scales linearly with the number of dimensions or variables, which is a huge advantage. The next question is, during solving the Burger's equation with HDES, is there any difference between simulation results running on IBM versus AWS IonQ? This we don't know yet. So at the moment, we have solved it only on IBM quantum computers. And because we have limited credits for both sets of computers, I think probably when we run on AWS, we won't replicate the same results, just because it's very important for us to try to do as many different simulations as possible. So, but it's a good question, actually. Perhaps we should compare the 2 sets of quantum hardware side by side and see how they compare. But I can't promise that that's something that we will do. And as far as we haven't done it yet, as far as I know. And the last question, can we use a Taylor series too? I'm not sure if I fully understand. As far as I know, it's not like a Taylor series. I don't know. I would need to look into it. It needs to be like a set of orthogonal basis functions over some domain, and it's not occurring to me right now if you can extract that from a Taylor series. So I'm not sure. Sorry about that. So just to go back, the one that I wasn't too sure about the meaning, I'll just try and interpret it. So Gerardo Suarez says all the scalings you mention is about mapping ODEs to the wave function, right? So the workflow would be taking PDEs to ODEs, and then the number of ODEs would be what correspond to the number of qubits. So just to clarify one part, we don't translate the PDEs into ODEs. We solve the PDE system as a whole, and the number of qubits corresponds, it depends on many things, but one of the things it does depend on is the number of variables. So you could say that's sort of like the number of ODEs here. But it also depends on many other things. For example, most obviously, the complexity of your equations and your solution function. So if you have a very heavily varying random solution function that's not smooth, you're going to need more qubits because you're going to need more basis functions to represent the result. And then, but there are also many other features. For example, like the basis that you choose has an effect on how many qubits you need and so on. So that really varies. So, and thank you very much for the very nice comments here. I really appreciate it too. Thank you very much for listening to me.